Great. Hi, everyone. Welcome to the Purdue Computational Imaging Seminar. And it is my great pleasure to introduce our today's speaker, Dr. Emma Alexander. Dr. Emma Alexander is a postdoc in the Vision Science Department at UC Berkeley and will be joining the Computer Science Department at Northwestern University as an assistant professor in 2022. She received a bachelor degree in physics and in computer science from Yale in 2013 and a master and a PhD in computer science from Harvard under the advisement of Professor Todd Ziegler. She has received the NSF Graduate Research Fellowship, the ECCV Best Student Paper, ICCP Best Demo, and the Berkeley CIVO Postdoctoral Fellowship. And she will present to us today the differential defocus in cameras and microscopes. Go ahead, Emma.
Thank you, Chi. Welcome, everybody. It is really exciting to be out here. Ever since Chi joined out there at Purdue, I've been super excited to meet you all because the work that I'm going to be presenting today sort of springboards off of work that he and I did working closely together in grad school. So very excited to finally meet the team out at Purdue. I'm very excited about you all. And today I'm going to be talking about differential defocus and how that is useful in both cameras and microscopes, how it's similar and how it's different. So just to start out, cameras and microscopes are both hugely important. They allow us to see and record important physical phenomena in the world. And they are similar in that they're both using light to collect that information. But it turns out that there are a lot of things that are different about them as well, which we'll be digging into in great detail today. And a lot of what we're going to be looking at today is pulling out those differences and putting these two imaging modalities on even footing so that we can directly compare methods in both. Now, if you're used to working with photography, like I was in my PhD, or if you're used to working in microscopy, like the lab that I joined for my postdoc, it turns out that you will form a lot of intuitions about how the world works and what imaging is and does. And so we're going to turn this into a math problem at the very end, but mostly this is going to be a communication problem, right? So the whole problem here is whether you're used to thinking about microscopes or used to thinking about cameras, you will have certain pictures that live in your head. These assumptions usually go unstated. And so most of the problem today will be pulling out and stating those assumptions explicitly so that we can actually directly compare these two methods. Okay, so how to get camera people and microscope people to talk to each other productively is really the goal of this kind of project. So we'll start out by defining simple models of what both cameras and microscopes are. So here's going to be my very simple model that I'll use. So a camera is a lens with an aperture placed in front of a photosensor. And for microscopy, I'm going to be talking about mostly 4F microscopy, applications-wise looking at mostly phase microscopy. So for a 4F system, you have two lenses, and they're separated from the object, the aperture, and the photosensor by a distance that matches the focal length of those lenses. So it's a little bit of a more specified, complicated beast. And I'm just going to throw up this bright red asterisk here because these are simplifying assumptions. They're not necessarily going to be true in all cases. And I'm just going to be sort of taking this general, what is a person who's thinking about a microscope or a camera? What's the picture in their head version? So we're going to be ignoring a lot of the fine details and a lot of possible other ways of doing these things and just keeping to sort of the simple standard models. So here's my camera. Here's my microscope. The first thing that immediately pops out of these sort of geometrical configurations of apertures, photosensors, and lenses is that they'll have a different projection. So if I have this scene, right, where I have two blocks and they're a different distance from each other, and I image them with the camera on the left and the microscope on the right, I will get two different images. The camera is going to give me a perspective projection where the size of the objects in the image is magnified by their depth. And on the right, with my telecentric system, that depth magnification goes away, right? So right off the bat, they're going to be collecting information about the world differently just from this geometry. And while you're all sort of, thinking about your projective geometry and thinking back to your image formation models, I want to make a quick aside about focal length. So this has been a Zoom poll before, but it's 7:30 in the morning over here, and I thought a pop quiz would be a little unkind. So instead, I'm just going to walk you through the question and tell you how it went last time. So the question is, okay, I've got this simple camera. I have a lens, aperture, photosensor, okay? And if I take the exact same camera and I move the lens, the question is, do those two cameras have the same focal length, right? And the answers that you could give me are, yes, they do, no, they don't, or what are you talking about? Okay. And so the last time I gave this, we had about 2/3 of people saying that the focal length was the same, it did not change, B, and about 1/3 of people saying that we had about 2/3 of the people saying that the focal length was the same, 1/3 saying that the focal length changed, and a couple of people saying, what do you mean by this? Okay, and that was sort of interesting, right? Because focal length, that's sort of a basic, well-defined quantity in our field. We're all pretty well educated, right? If you're showing up to a Zoom seminar, you should probably know what focal length was. And so the fact that there was this big difference in what people thought was meant by this term, I think is pretty interesting. And we can trace it back to, I think, the background of the people who came into the field. So you probably said that the focal length didn't change at all if you are from an optics background. So if you go into an optics textbook, the focal length is defined as the inverse optical power of the lens. And so as you move this piece of glass around, the focal length travels with it. It doesn't change at all. But if you come from computer vision, you probably did think that this focal length changed, because if you look in these textbooks, they will define the focal length as the distance between the lens and the sensor. Okay, so all of this is to say that we have to be really, really careful about these pictures in our heads, because I was talking about focal length to a bunch of people who thought that I could not possibly be so stupid that I didn't know what focal length was. But actually, we were using the term to mean different things. And so I would argue actually that the correct answer here is, what are you talking about? And if you want to collaborate effectively across field lines, you have to be willing to ask questions that are as stupid as, what do you mean by focal length? Okay, so just to sort of—
Can I ask a question, Emma?
Yeah,
so
absolutely.
Okay, I'm like a Fourier optics person, so I think that the answer is no. But how do the vision people think about? So why is it depending on the length between your lens and the sensor? Why does it make sense to those people?
That's a great question. And I've had a lot of conversations with optics people, and it seems like basically the answer is that you guys are too good at your job. And so optical engineers have pretty much, as far as we're concerned, perfected lenses. We don't really need to worry about the optics of the system. We don't think too hard about like what's going on in the lens assembly. And so it's very common for computer vision people to think, okay, I don't need to worry about optics. I don't need to worry about aberrations. A lens is something that magically images the whole scene. And so the origin, I think, of this assumption is you say, okay, well, I'm going to focus my camera at infinity and I'm going to have a really large depth of field. And so everything's just going to be in focus. A lens is just a slightly nicer pinhole. And so I think that's sort of the origin story of this confusion. And there are some people, so like if you look at Bertold Horn's book, he gets it right? He only ever says, if you put this, if you focus this camera at infinity, this will be the distance. But then I think for the vision people, right, like we don't have to worry about optics so much, but we do worry about that perspective projection. And so if you take a computer vision course, you're going to see all of this projective geometry. And so people sort of bury this like really key assumption that that's only true when you're focused at infinity. And so if you look at a camera matrix, right, that's where this focal length comes in these textbooks, is the camera matrix is this like perspective projection operator. And you just say the focal length is like the depth-based magnification. But of course, that's not always going to be true. Even if for a lot of photographic applications, it's close enough to being true because you want most of the scene to be in focus. But for things like portraiture or macro photography, places where defocus effects are visible in photographic images, this won't be true. And so then you sort of have these two numbers that are vying for the term focal length, where both that sensor distance and the optical power matter. And depending on who you're talking to, they will assign that term to different parts of the camera.
Interesting.
Yeah.
Thanks for sharing this perspective. I was sort of unaware of the other perspective that people are thinking. So it's good to learn that. Yeah, just let me keep in mind. Yeah, thank you.
Yeah. One could also argue that, that focal length is a term from optics and that we should just learn to use it correctly. But I don't think that computer vision is going anywhere. And so I think that we need to sort of be able to translate between the two fields.
Yes.
But yes, this one tripped me up for a long time because nobody wants to admit or accuse someone of not knowing what focal length is. So just to sort of illustrate the depth of the communication problem that we're dealing with here, you really have to be very, very upfront about what you're talking about, more than maybe you realize.
Sophie has a comment. We need to change computer vision textbooks. So let's don't launch this kind of war. I think the computer vision textbooks are all fine, but it is sometimes it's about communicating with people. I think that's something that we as someone who are going to present work, I think we should be aware of that. Instead of saying that, you guys are blind. I don't think that's the right.
No, it is. There's a good argument that the computer vision side is wrong, but like the code that runs your cell phone camera, like when it talks about focal length, it's that distance that it's talking about because it's all of this perspective projection. So anyway, we're in a real mess, and I'm glad that that we can all agree that we're in a real mess here. So we got to be really careful talking to each other, but we've established this first difference, right? Which is that if you're talking to someone who's thinking about cameras, they're imagining perspective projection where the size of an object depends on where it's located. But if someone's coming from a microscopy background, that is not a part of their intuition. Objects stay the same size no matter where they are. Okay, so that's our first big difference. The next is going to be in the typical scenes that we image. So these are just some images, again, not set in stone, but sort of the general mainline intuition of people in different parts of these fields. So on the left, I have a typical photographic image, and on the right, I have a typical image for phase microscopy. So there's a lot of different kinds of microscopy. So this is maybe starting to get a little bit more niche in the assumptions. But the object on the left, this sort of flower scene, from a photography side, we would call this a Lambertian plane. So this flower is like an opaque isotropic reflector. So the model is that there's light coming in all directions and bouncing off in all directions. And we don't always assume Lambertian, we don't always assume planar, but usually lurking in the back of our head is the idea that the world is like basically flat and basically, reflecting light in all directions. That is very different from this sort of like transmissive phase microscopy setting where you have a phase object. So the object that I'm showing here are some cheek cells. They're clear, they're not stained, they're not labeled in any way. And so light moves through them and gets deflected. And the deflection of this coherent illumination gives you those slight brightness variations around the edges of the cells and their sort of little organelles and stuff. So I want to be clear that you could take the object on the left with a microscope, you could take the object on the right with a photograph or with a camera, but you would be violating some basic assumptions, and the way that you would think about it would probably be pretty different. So while a photographer would think of this flower as basically Lambertian and basically planar, someone from the phase microscopy side would think of this as like an ensemble of mutually incoherent point sources, or perhaps like an amplitude mask that's illuminated by an incoherent source, right? They're similar ways of getting at the same idea of light is moving in all directions, but the way that people think about it is very different. Similarly, to take a phase object in photography, we would think of that as like a glass or a fluid, right? It would be sort of an unusual sort of spicy object to be taking a photograph of. And so, the basic scenes and assumptions that we make about the world will also be different depending on which side we're coming at this problem from. Okay, so the picture that you have in your head is going to be very different, not just of how your imaging system works, but also of how the world works and what the world looks like. Okay, so we've got these two differences now. So we've got the different projections and we've got the different coherencies, right? So the camera will be observing generally some incoherent scenes. So all the points will be spreading out light in all directions. Whereas for the 4F microscope, we're going to assume for this phase microscopy application that it's observing coherent illumination just moving in one direction. So I promised in my abstract a gentle introduction to coherence because it's a tricky topic and one that certainly on the photography side, we don't ever really think about. So what is coherence? If I am sitting at the peak of a wave and I take a step in space, if I can still tell you where along that peak and trough I am on the wave, that's spatial coherence. So the sort of poster child for spatial coherence is a plane wave. That's that everything is moving in the same direction. Similarly, if I'm sitting at that peak of the wave and I take a step in time, right, I just sit there and I wait. If after that time step, I can still tell you where along the wave I'll be, that's temporal coherence. And temporal coherence, you should think of this as like the monochromaticity of the light. Now, these are two interrelated but separate phenomena. So if I have a light bulb, I can think of that as incoherent. And if I have a laser beam, I can think of that as coherent. And that's in both senses, right? So in terms of the spatial coherence, the light bulb, the light spreads out in all directions, right? So that's showing that it's spatially incoherent, while the laser beam should stay very tight and small. And then the temporal coherence can be measured from the spectrum. So the sort of broad spectrum that I'm showing there for the light bulb should be very different from like a sharp peak for the laser. And in terms of what people mean when they say the word coherent, this one is really tricky. A lot of times people will just say coherent illumination and they won't specify which kind they're talking about, and they won't specify how coherent it is. There are types of illumination that might be considered coherent for some application spaces or some scales, but are not considered coherent enough to be called coherent in other ways or for other problems. And so sort of knowing what people mean when they say coherent is really, really tricky. When I talk about coherence for this talk, I'm going to be pretty much ignoring wavelength. So we'll just assume it's monochromatic, right? So perfectly temporally coherent so that we're only worrying about one wavelength at a time. I'm going to think about the coherence mostly as the number of directions that light is propagating through the scene. So that's a measure of spatial coherence. So when there's one direction of light, I'll call that coherent or spatially coherent. And then as we add different directions, you can think of this as like, you know, fanning out a bunch of lasers to sort of add up to that light bulb. That's the sort of model that I'm going to have in my head of how we move from coherence through partial coherence and into incoherence. Okay, so why would you bother with coherent imaging? If you're from a photography standpoint, like you might not really know of any applications for this, but a really important one in microscopy is phase imaging. So if I have this coherent beam coming through my scene, right, I've got all of these nice lined up wavefronts. It's that one color in green, it's that one direction, so it's spatially and temporally coherent, and it hits this prism. What's going to happen is at the top of the prism, it's got a lot of glass and it slows it down a lot. But at the bottom of the prism, it doesn't have to go through much glass. And so at the bottom, it'll get a head start and the beam will be deflected, right? Based on the thickness and refractive index, which combined together give you the phase of this object. So you can imagine if you took a picture of this undeflected beam, and then you said, okay, well, I put my prism in and this beam gets moved, right? You can imagine pretty easily that you could recover the phase profile from this image information. In practice, prisms are not that interesting as objects. So usually what happens for these microscopy applications is you'll send this wavefront through a complicated object like a cell, right? It's sort of like this weird squishy bag of water and other things. And you'll get this weirdly shaped wavefront coming out. You'll collect images like the one that I showed before of this scene. And then it's a little more complicated. We'll get into the math in a minute. But then you can reconstruct the phase profile of this more complicated, more interesting object as well. Okay, so that's like the whole game of phase imaging with coherent illumination. But today we're going to work on moving that idea into a regime of partial spatial coherence. Okay, so when I say partial spatial coherence, right, we had our one beam that was deflected by the prism. And so we can think of this in phase space. So this is, I've got two sort of plots here showing X and U. U is the direction. And so the beam coming in is shown as the white line on the left, where, I'm in, 0 direction. And then once I pass through that prism, I have now moved so that everywhere along the line, everywhere along space, I'm now moving in a slightly deflected position. Okay, so now what happens when I send multiple beams through the same object? Well, that's pretty simple, right? They're both going to get deflected by the same amount. And so, we can just sort of imagine building up sort of a probing of this scene where we can, send beams through and record what happens. And if you're from a photography perspective, you might be thinking, wasn't this just a light field, right? This is a spatial angle representation of this scene. And the answer is sort of, right? So what this gets you that is like a light field is this space angle representation. But what you're missing here is that there's no ability to capture wave optics, right? A light field is purely scalar. You can't have any kind of diffraction or negative or destructive interference because there's no negative values, right? All you can do is add light. And so basically you can think of this as, if you're doing it correctly, a light field with negative values. And the proper mathematical formulation of this is in the Wigner distribution function. This is a super useful, friendly, really, really nice way to think about imaging problems. It's not used very often, and I think that this is why. So this is the definition, and it's kind of a beast. It's the Fourier transform of this time average mutual intensity, right? So it's like you're taking this shifted autocorrelation of the field with itself. And I think this scares a lot of people off, but I really like it, and I think that it's really nice. I think we should think of this Wigner distribution function as like a box, okay? And it's a really good box, because what it does is that it lets you put an electric field into the box, okay? And this big kind of nasty equation just tells you how to pack the box. But once it's inside of the box, you can move it through the scene really, really easily. So you can just use ray optics to propagate the Wigner distribution function through free space or through optical elements. It's like very, very convenient, as a way to approximate rather than like having this like super, super high resolution Fresnel diffraction propagation. Like, it's so much nicer. You're using ray optics math to do wave optics propagation. And then once you get to the end of it, based on how you packed the box originally, you can then unpack the box and get an image out that is wave optically correct. So this is like a super, super, really nice, friendly, powerful mathematical object that I'm a big fan of. And we need it to attack this problem. So if you want to learn more about it, there's this textbook if you're from the optics standpoint, or if you're coming from a computer science background. These two papers are particularly good at connecting them to the light field, which a lot of us have more intuition with. So just to sort of steal a figure and walk through from the second paper there to build up some intuition here. So if we have a plane wave that encounters a pinhole, the light field picture there is that after that wave encounters the pinhole, there will be some small spatial extent, and then the wave will continue moving at just the angle that it came through in, right? So that's that little spot at the origin in the light field picture. But in the Wigner distribution field picture, we know that actually the light is going to diffract out from that pinhole, and that you will get energy propagating in multiple directions and not just, cutting off the plane wave to a smaller spatial extent. So this is sort of a picture of the way that we sort of slightly alter our light field intuition to account for wave optics. If you have two pinholes, this one's pretty cool. So now we have the two vertical red bars. That's the diffraction through each slit. And then in the middle there, the blue here represents negative values. So this is going to be your interference term. And so this is what lets you sort of move these negative rays around, right? And still get things like the double slit fringe interference patterns here. Okay, so we can represent diffraction, we can represent interference, and just to sort of get us into a more sort of complex, starting to be physically really sort of meaningful picture. Here's a rectangular aperture. So on the right for this light field picture, after you go out of a rectangular aperture, again, you're not going to get any new directions, and you're just going to have some wide spatial extent. Whereas in the Wigner distribution function, you can see that, as you get to the edges, you're sort of approaching that vertical red bar like a point source on each edge, but then within the middle, you're mostly getting sort of red positive light through, but then those blue fringes around will properly capture all of the diffraction through that aperture. So super cool, pretty easy to sort of upgrade your light field intuitions from photography into this sort of more optically correct picture. Really cool, useful object. And we're going to use it to generalize the notion of phase. So, well, that's a pre-existing idea, but it's something that we will be using. So if I have this beam that gets deflected by a prism, right, at any point in space, I can sort of say, what is my phase? Because there's this one wavefront that's propagating through the scene, and I can sort of pinpoint where I am along that wavefront. Okay, and we sort of noticed, right, from this little linearized model that the phase slope will give you the direction of the beam. And we can actually reverse that intuition and use it to define the phase. So if I know my direction u that I'm propagating, I can say that, okay, well, the phase of whatever my object is just the thing whose slant gives me that direction. Okay. But if I'm in a partially coherent, even the simplest partially coherent situation here, if I'm at some point in space, I no longer have a well-defined phase, right? Because there's two waves moving through the scene. And so I can't pinpoint with a single number where I am along both of them, right? It becomes a sort of undefined quantity. And so to generalize the definition of phase for a partially coherent scene, we're going to take the average direction. So what I can do is I can say, okay, well, the average of these two beams, right, for whatever that means, is like the single wave propagating through the scene, and then I'll just pinpoint where I am along that wave. And the question then becomes, what does it mean to take an average of multiple directions of light moving through a scene? And for that, we're just going to say, okay, well, the average direction will be weighted by something like radiance, right? So if one beam is much, much stronger than the other, it should be weighted more. And the sort of wave optically correct way of getting the weight or the radiance at any point in a scene is this Wigner distribution function. And so, this phase space object that I showed you before, right, these WDFs before, where on the left we have two beams coming in and on the right they're both deflected, you can just sort of take the weighted sum along the u direction, and you would get this intermediate direction through there, where, if you had more beams in one direction or more power going through in one direction, it would shift that center of mass appropriately. Okay, and of course, in the simple case where we only have one direction moving through the scene, this Wigner distribution function is very simple, and this does reduce to the traditional direction of phase. Okay, so just to sort of zoom out for a second, we introduced this complicated mathematical object. It's very useful because it lets us move things through the scene using ray optics. It lets us think about wave optics as if it were ray optics, right? And so that lets us connect the intuitions between photography and microscopy. And the way that we're going to sort of use it mathematically is to let us count up how much light there is at any place in the scene, which will let us generalize the idea of phase to situations where maybe the phase doesn't actually make sense as a physical quantity in and of itself. Okay, so where are we at? Cameras and microscopes have different projections. They have different kinds of illumination typically, and their objects have different kinds of properties. So we've been talking about phase microscopy because microscopes oftentimes will observe objects like biological tissues that have this well-defined phase. Whereas photographic objects don't have a super well-defined phase. That's not how we talk about them. Instead, we talk about them having depth. And so what we want to do is we want to take these different assumptions and these different like relevant scene factors and connect them so that these two paradigms can talk to each other. And the way we're going to do that is with defocus. So for either a camera or a microscope, there is some depth in the world that will be in focus. And we'll take them out of focus by moving the camera or the object to put them out of focus. And I want to point out that this is another place where cameras and microscopes are really different. So if you want to defocus a camera, there's a bunch of ways you can do it. You can basically change anything on here and change the amount of focus. So the picture that's being carried around in a photographer's head about defocus is going to maybe be different, even depending on what application they're working on. So if you're used to sort of a big SLR where, you know, you turn the ring and that changes the focus of the camera, what that is doing is it's changing the lens location. If the camera, quote unquote, that you're used to thinking about is, for instance, the human eye, if you talk to someone who works in vision science or optometry, their sort of go-to focus mechanism is going to be the power of the lens changing, right? So the shape of the lens in our eye changes. And that is how you and I are focusing on the screen right now. Other animals will defocus their eye by changing the location of the retina. You can also, this was common in early depth and defocus work, you can just sort of squint down and change the size of the aperture. That will change the overall scale of the blur, although it won't change the sort of fixed in focus point. And of course, the one that I mentioned before is that you can change either the location of the scene or the location of the camera so that the relative depth is different. And I'm not going to go into the details on this, but all of these can reveal the depth of the object. Worked through this in my dissertation, and Chi and I built some great prototypes of a few of these. But the basic lesson is that a camera is a simple object, right? It's a lens and a sensor, and you can basically fiddle with any part of it and still have a camera, just with a different amount of focus. A microscope, however, is a more complicated object, right? This is a 4F system. And so if I started changing the optical power of something or the distance of something else, the whole rest of the system would have to change to accommodate that in order to stay a 4F system. And so really the only way to defocus a microscope without like some really complicated interrelated factors is to change this scene to system distance. Although in practice, a lot of times this first focal length is much, much smaller than the second, because that's where you get your magnification. And so a lot of times you can just move the front lens and that becomes similar to moving the entire system. Okay, so even just, you know, how do you defocus, or are there many ways or one way to defocus is the difference between these two settings. But now we've got everything we need. Okay, we understand how they project. We understand how they're illuminated. We understand what they're looking at and what matters about the things that we're looking at. And we know that there is one way in common that we can defocus both of them. We can take a step in depth. Okay, so now we've done a lot of the breakdown of the communication. We're gonna transition into math mode real quick. But first, I just want to give you sort of a high-level overview of when we combine all of these, what we look like. So these are the images that we've seen from the camera and the microscope. And here's what it looks like as they come into focus by changing the depth of the sample. So here's our perspective projection coming in as the flower gets bigger, right? And then we're going to retrieve these like high spatial frequency features on the petals, right? Out, it's really blurry, low spatial frequencies. Then it gets bigger, high spatial frequencies emerge. This is how photographers think about defocus. On the microscope, it looks really different. So these are these cheek cells, and we're going to be zooming through. So we'll be out of focus, into focus, out of focus again. And we'll notice that this is really different, right? We don't have that perspective projection changing the size of the object. And we also see, rather than just like losing high spatial frequency content throughout the image, these ringing artifacts can actually create new high frequency image content, not field content, but image content. You can create high frequencies in the intensity as you go out of focus. And so this is really, really different. This is actually a huge surprise to me when I learned that like defocus didn't always just blur. This kind of blew my mind. Okay, so we have a picture of what images look like in both settings. We have a picture of what defocus does to those images in both settings. We sort of understand where it comes from and why these things are happening. And I keep telling you that we can tie them together with a depth step that creates defocus. So what does that actually look like? Okay, it turns out that in the sort of large scale depth step, these are very complicated problems, but they're simplified by taking a differential step in defocus. Okay, so we can ask for both the photography and microscopy settings that we built up, what happens when the object depth changes just a little bit. Okay, so in the camera setting, this is described by depth from differential defocus. This is a lot of work that she and I did together. And so I'm going to walk you through this equation, okay? This equation says that the intensity change in the image, right, di dz, as you take a step in depth, is going to be the sum of two terms. In the first term, it depends on the object depth, the location on the image x, and the first spatial derivative of the image. This is going to be the like optic flow expansion field, right? This is going to account for that perspective projection that changes the size of objects as we approach them. The second term is going to depend again on the depth. There's a constant c, that's not the speed of light, it's just a constant. It's calibrated out of your camera, and then it depends on the second spatial derivative, right, the image Laplacian. And this comes from the fact that the blur scale is changing as your defocus changes. And if you have Gaussian blur specifically, the second spatial derivative of that is going to be proportional to the scale derivative, right? So as I change the scale of my Gaussian, that's going to be just a scaled copy of the spatial Laplacian of that Gaussian, and the amount that it's scaled actually encodes the depth. Okay, so what this equation says overall is that if I have, if I take an image step in a camera and it's small enough, right, if it's differential, I can say, okay, well, I can measure what that change was. I can measure the first and second spatial derivatives of the image, and then I can sort of, you know, combine those quantities together to pull out the depth that is in their relative coefficients. Okay, so this is a depth recovery method for photographic settings, and it's just combining a differential scale change with a differential defocus change under the assumption of Gaussian blur. Okay, it was pointed out to me that this equation looks a lot like a microscopy equation called the transport of intensity equation, or TIE. TIE is a little bit different, but it's got some pretty important similarities. So on the left now, we have the same intensity difference as we take a step, di dz, right? We saw that before. Now it's scaled by this wave number k, right? That's like the inverse wavelength for folks who are not on the wave optics side. And again, this is going to be the sum of two terms, both of which involve spatial derivatives of the image. And now instead of depth, we've got this phase phi, okay? And sort of on first glance, it looks like these two might be related. If you sort of say, okay, well, phase is like depth, then actually they contradict each other. And so there's sort of this question of like, how do these relate to each other? But first, I'm going to walk you through where these two terms come from. Okay, so let's say I've got this wave front, it's propagating downward, right? And I'm going to take a differential step with my sensor, where I'm going to take an image at those two gray planes. So the first term here says that, well, you know, if I've got a brightness change, right, an amplitude change, an intensity change across di dx, and I've got a slant in my local phase, then that intensity, right, that sort of texture of the image is just going to shift, right? This is just like a first Taylor term. So we're sort of shifting the image intensity pattern across depending on our local slants. And then the sort of second Taylor term here is that, well, okay, also, if I have a local curvature in my wavefront, then I'll have an overall growing or shrinking of brightness due to local lensing, right? So if I've got this positive curvature here, then light will sort of become focused at that point. If I've got like a diverging wavefront, the overall brightness will diminish. And so this transport of intensity equation is giving you this first two Taylor term approximation of what this wavefront is going to do to image intensities. Okay, so we now have an answer for each setting of what happens when the object depth changes a little and we get a differential amount of defocus. And now we want to sort of start to put these into conversation with each other, right? So we understand why these are different. And so to sort of pull them into each other, we're going to find an intermediate setting. So we'll assume that we have a differential defocus change. And now instead of using our camera and our microscope, we'll assume that they're both telecentric systems to remove that expansion term. And we'll put them into a place where they're looking at partially coherent illumination, right? Where there are some number of directions of light moving through the scene. And this sort of pulls them in towards each other and lets them talk to each other. And so then we can ask, okay, with these new assumptions, what's happening? Turns out that TIE, it's a very general equation. It holds for those assumptions as well. The depth from differential defocus picture changes a little, right? I mentioned that telecentric system will remove the expansion term. And so now we just have the intensity change is only caused by this, this defocus change, which relates to the second spatial derivative of the image. But of course, that relies on this special mathematical property of the Gaussian, and also it's not going to work unless you have objects like these photographic objects where you have light in a lot of directions. So I said we're partially coherent, but if you're towards the highly coherent side, these assumptions are going to break down. So you have to be pretty incoherent for this to hold true. So our assumptions here are just the paraxial approximation, Gaussian blur, and a pretty high level of angular isotropy at some well-defined depth z, right? So if we don't have that angular isotropy, it's hard to say where the object is, because that's just sort of how we define depth for like a point source or a photographic object, right? It's where all of those like cones of rays originate. As I mentioned, the transportive intensity equation already works for the partially coherent case. It's just that now that phi, instead of standing for the traditional definition of phase, now stands for that generalized version of phase that we described with the Wigner distribution function. So this applies equally well in this setting. And all we have to assume is the paraxial approximation. So now we have these two systems, and we can ask, if I take a step forward in depth, what happens to my brightness? I have two answers. One of which makes a lot of assumptions, and so it's a special case, and the other of which actually doesn't assume anything. So it applies regardless of what I'm looking at, and it's a more general case. So we can think of depth from defocus as a special case of phase imaging, as long as we're allowing this generalized definition of phase. So what does that mean, right, for this to be a special case? We'll dig into the math real quick. So this is going to tell you how we take those two assumptions, the Gaussian blur and the large number of directions in the scene. We'll take TIE and turn it into our depth from equation, our depth from defocus equation. Okay, so what does it mean to have a Gaussian point spread function? That means that if we have a point, it turns into a Gaussian. And a point source in this sort of paraxial approximation is just a quadratic wavefront. And our Gaussian image just says, okay, I should have this, Gaussian profile of intensity, right? So this is pretty straightforward. This is just saying a point goes to a Gaussian image. And you can notice that there's this x squared term in both of them. And so in this case, it happens to be that for a single point source with a Gaussian blur, the phase of that object is proportional to the log of the image intensity. This looks coincidental, right? This is like not a super strong observation on its own, but it turns out that if you go through the math, the angular isotropy at z, right, which is something that you get from a depthy object, so something like a Lambertian surface or a collection of these mutually incoherent point sources that have a well-defined spatial location, as long as you have this feature, which is to say that in phase space, you have this sort of constant slant in your brightness distribution, if you combine that angular isotropy, so that well-defined slant that continues over some neighborhood of space, with this Gaussian blurring in your angles, this sort of coincidental connection that we notice actually does hold for all scenes like this. So the generalized phase for a Gaussian blurred low coherent scene is proportional. The generalized phase there is proportional to the log of the image brightness. And it's also proportional to the depth of the scene. So this is really important because this means that no matter what our image texture is, we can correct for that by just dividing out the log of the brightness, right? And we don't even need to know the in-focus texture of the scene, just the blurry version that we collected. So we can, just divide that out, and then we're left with a depth measurement, which is pretty cool, right? So to sort of show that simplification from general to simple, or to special case, I'll just walk through this really quick. So here's the transportive intensity equation, which I flashed up here a couple of times. We sort of saw on the last slide that we can express our Gaussian point spread function and our low scene coherence assumptions together as this restriction on the generalized phase, right? Where it's this combination of the depth and the image intensity. And if you just plug in that definition of phi into this equation, right? If you just take the first and second spatial derivatives of this, you can work that out on your own on a sheet of paper, but you can also just trust me. This gets you directly back to this new depth from differential defocus equation that I showed you before for the microscope case where we have a telecentric projection. So this is really great, right? Because it says, oh, I can find the depth of my objects just by dividing out the two image brightness derivatives, which are very quick and easy to measure. And then, scale that by the width of my Gaussian, and boom, you're done. So this is a really great, efficient depth measurement algorithm. It's worth noting that it is not the only depth recovery method suggested on this slide. So if we take our phase assumption for photographic-like scenes, we can see that actually another way to measure depth is to note that this generalized phase is proportional with depth and some known quantities. And so what you could do is you could use TIE or some other phase recovery method that gives you this generalized phase, divide out the log of the image brightness, scale that by some calibrated constant, and you'll get out the depth of the scene. Now, computationally, that is a dumb thing to do, right? By the time you've recovered the phase, you could have just gotten the depth directly from image derivatives. It's hard for me to imagine a scenario in which you would actually want to calculate things this way. But in terms of like a revealing mathematical connection that helps us understand these two settings better, I think it's really interesting that now we have a way that a phase measurement can be upgraded into a depth measurement, provided that that is the kind of information that is available in the scene that you're looking at. Okay, that's a lot of math. What does it all mean? It means that you have this transportive intensity equation, and it describes the generalized phase. Okay, and when the image content is coherent, when you have coherent illumination and you don't have anything fluorescing, you're just doing this sort of standard phase microscopy piece, that generalized phase that you recover is just the scene phase, right? But when the image content is incoherent, right? When you're doing phase imaging on an object that is not appropriate for phase imaging, this Gaussian blur assumption allows you to reinterpret that generalized phase as a depth measurement, which is pretty cool. So this is like a neat mathematical connection that we found. Of course, we have to ask if this is useful. The answer to that question so far is maybe. So we know that on both ends of the spectrum, this is a very useful way of doing things. So these are Cheese Austin sensors that do depth from differential defocus. We've made some of these prototypes, and they can give you really good depth measurements at 100 frames per second on a laptop. So it's like a very, very efficient way of getting out the depth, which is great. TIE also, very cool, important method. So this is nifty. I just stole this figure from a paper. It's taking a video of a cell that is like eating another cell. And so you can very quickly, without staining, without treating this object in any way, you can recover its, to some extent, its 3D structure, right? That's sort of what phase is getting at. And you can observe these tiny organisms doing their thing without disturbing them. So on both ends of the spectrum, really useful to do these differential defocus methods. In the middle, we're not really sure yet. So, right, so this is going to be like in the partially coherent regime. So I'm just going to show you a quick simulation that we ran of like what the sort of partial coherence we're assuming does to both of these methods. So, so here's our telecentric 4F microscope, and we simulated an object that has a couple of bumps in phase and this sort of chirp pattern in its amplitude. Okay, so we're going to get amplitude stripes and phase bumps. And we can imagine this slightly out of focus and then taking a differential step in defocus. And we can imagine what that looks like if we illuminate this object with a single coherent beam, or as we sort of expand the angular extent of this illumination to become less coherent, right? So this sort of wide beam that I showed you would be appropriate for depth from defocus on the left. And then, as we sort of shrink down in our coherence, we're going to get closer to the sort of native domain that phase microscopy TIE is usually useful in. And so here are the Wigner distribution functions for these objects. We sort of see there's two kind of slant encodings in here, right? So just like an intuitive way to read these phase space diagrams out is that the slant of those sort of chirp stripes gives you the depth of the object, and then the angular change is going to give you the derivative of the phase. And so you can sort of see that as we shrink down our beam, as we become more coherent, those depth stripes become less easy to determine, and the phase information becomes more predominant. Sort of the other way around is that on the left, as we have this really pretty incoherent setting, the phase stops mattering, right? You don't see that jagged line anymore. And so if we sort of simulate a phase and depth recovery, we can see that, so our phase bumps here are in the blue is the generalized phase that we recover. And we see that in the coherent case, that generalized phase is just the object's phase. But as we lose coherence, the generalized phase stops resembling the object at all, right? That's just those sort of blue bumps there. But on the other hand, our depth measurements in green are much better when we have low illumination coherence, right? So we sort of, as we move to a more coherent setting, we get better phase, but worse depth estimates. And we think that there might be some settings, maybe you're trying to do really fast microscopy where like something is moving around, it's swimming, you want to measure its function over time, and maybe some things are fluorescing. So maybe there are some settings where you have partial coherence or spatially varying coherence across your image, and getting a really rough estimate really fast of both of these things could be useful. But at the moment, we're not really, we haven't built it into a robust application yet. So the things that we learned today, we learned that differential defocus is useful both in microscopy and photography settings. But if we want to connect across those settings, we have to recognize assumptions that we're making about the optics, about the illumination, about the objects, and even about like really basic things like when we say words, what we mean by them. We also learned that depth from defocus in computer vision can be seen as a special case of phase imaging from defocus in microscopy through the TIE equation. We learned that the generalized phase reflects the object's phase when we're in coherent settings, but it also, importantly, novelly reflects the object depth when we're in incoherent settings. And we learned that the Wigner distribution function is a very powerful and important mathematical object. So with that, I would just like to thank all of the folks that contributed to this work with me, especially a big shout out to Chi, who was really fundamental in getting the camera version of this off the ground. So thank you all for listening, and I'm happy to take questions.
Thank you so much, Emma, for the great talk. And let's applaud for the speaker. And feel free to just unmute yourself. If you'd like to, you can also have your video on, like ask any questions you'd like. So I see Babdi, you can first go ahead.
Yes, my question is regarding defocus. When we deal with, can you hear me? Sorry.
Yes.
Yeah, when we deal with large, big objects, part of the object will be focused, part is not focused. So how is this going to relate your findings? Is my question clear? So
no, it is.
Focus is always a problem with big object in the axis of the camera or the microscope.
Yes. Yeah, I think that's a really great question. And it's one of the big sort of missing assumptions that I didn't go through. So I think this relates actually to Stanley's question earlier about, how is it that like computer vision people have such a different definition? One of the big differences between photographic and microscopic applications is that usually in photography, we have really large scenes and really large depth of field. And so a lot of computer vision just ignores depth of field. It assumes that everything's perfectly in focus. Whereas for these microscopy applications, you tend to have like very small depth of field. And I think that is going to be important as we sort of try to get into this sort of practical middle regime where the sort of even just like the scale of the step that you should take for the defocus in cameras or in microscopes is very different. So for TIE, you want things to be basically in focus and you want to take a very small step. For the camera size, we never found the optimal step size in defocus, mostly because when we were looking at photographic scenes, everything that we picked worked. But I do think that there's something underlying here that we have not teased out yet, where the step size that you're going to want to take for both of these methods is different. So it's a really good point, and it's something that we haven't gotten into yet.
That's it. Thanks.
Is there any other questions?
Can you comment about this trade-off between depth and also the phase accuracy? I'm trying to follow. It's like an uncertainty principle, but somehow I wasn't able to pick up the idea, right? Why are you sacrificing the phase with the depth?
Yeah.
That.
Perfect. Okay. Yeah. So the idea is that so this blue curve here, where when your illumination is very coherent, the generalized phase that you get is just the same thing as the object phase. But then this is actually, these blue results aren't even from like a failure of TIE. This is literally just like the ground truth generalized phase. As you add in more directions, you start getting that like that slant because the object is defocused. And so then the sort of, if you think of the generalized phase as this thing that's defined by like the first moment of the Wigner distribution function, then as you sort of have these slanted blobs, you're like moving where that moment goes. And so you're accumulating these features in like the ground truth generalized phase that sort of bring it away from the object phase. So we're not getting into anything as like precise as, what is the sort of uncertainty principle best possible. This is just when you add more directions into the scene, you no longer have a well-defined phase. And so you have to substitute that with some mathematical object. And this generalized phase that the TIE recovers has this issue where if you're in a low coherence setting and slightly out of focus, then the generalized phase of the scene is not going to match the phase of the object very well anymore. Does that answer your question?
Yeah. So can you comment about the two extremes where your illumination is completely coherent versus is completely incoherent? Would you, on the one hand, you get a perfect phase, the other hand, you will get a perfect depth, or even yeah.
So assuming that you can perfectly recover, like just ignoring all noise and algorithm problems, assuming you can perfectly recover the generalized phase. What this is saying is that you get the generalized phase, and if you're perfectly coherent, then that is your object phase, and that is the correct way to interpret it. As you move into a less coherent setting, you'll get this sort of in-between value where like the ground truth generalized phase neither corresponds with the original object phase, nor has like it doesn't really have a physical interpretation at that point. It's just sort of this like, okay, this is what TIE gives you. It's this weighted sum of the phases. But then once you get into the fully incoherent case, we say, oh, now it has physical meaning again. it can be reinterpreted as a depth measurement.
Oh, very cool. Thank you.
Thank you very much. I see Magdi with your hand. If you can, like,
oh yes. Sorry, I have another question. It looks like you ignored the wavelength completely. So
Yes.
when we go to RGB or hyperspectral imaging,
Yes.
how does your finding capture those kind of images?
Yeah, that is a great question. So this derivation is totally ignoring wavelengths. So we're assuming everything's monochromatic and simple. There are multiple wavelength versions of TIE, but they're kind of messy. There's like a nice way that this phase is sort of an elegant extension, and the extension over wavelengths is just sort of like, okay, you sum over wavelengths. We've never done our version with RGB. We've always just used a monochromatic sensor, which is obviously collecting across the whole spectrum. And again, we just sort of found that it worked. The camera version of this is like remarkably robust to a lot of different physical factors, to a level that honestly we can't explain yet. So yes, if we're being very precise about it, these are only explored in the single wavelength case. I don't know that there's a way to, like, you sum over wavelengths and it gets just sort of inelegant and messy. I haven't seen anything really insightful about how to do that change. But luckily, we find that in the camera case, we can just sort of ignore it and get away with that. But in terms of moving it to RGB, I think that there probably is room for improvement there for sure.
I see.
Thank you so much. We are slightly out of time. Just to let everyone know that we still have a couple slots to meet the speaker today. If you would like to discuss with the speaker one-on-one for like about half an hour, please let me know, or let Stanley know, that we will arrange it for you. And let's thank again the speaker for this wonderful talk.
Well, thank you very much. Thanks a lot.
Thanks, guys. It's great to be out here.
Great.
Thank you, Emma. Thank you very much for coming virtually.
All right. I'll see some of y'all soon.
Bye.
Bye.